Hi, everybody. Welcome back. In the last few videos, we introduced the ideas of molecular dynamics, which can be used to explore protein conformations and solve ultimately or hopefully for the native state of a protein simply by simulating the folding process, trying to mimic what would happen in a natural system. And if we wait long enough in a simulation, hopefully we find the global minimum solution. That can work, and there have been successes using this approach. It's expensive, however, and one of the reasons for it being expensive simply comes down to the time scale of protein folding. Protein folding for the very, very fastest proteins occurs on, say, the millisecond time scale, whereas for and many proteins fold up to seconds or even minutes or longer time scale. But in simulating molecular motion, we have to take time steps in the integration schemes that are small enough to capture the low-level atomic motions. That generally means that we have to take time steps on the order of femtoseconds. And just that difference of scale, if you have to work on time steps of femtoseconds, and yet you wish to calculate trajectory over milliseconds or seconds, that's a vast amount of computational time required. So perhaps there's other ways to explore the conformational space to find low energy states that doesn't require mimicking the actual folding pathway. Maybe there's something that we can do more quickly. So in the next few lectures, we're going to introduce some of the ideas underlying alternative approaches to exploring an energy landscape, finding low energy states in such a landscape. So let me begin by switching to the whiteboard. And then moving from here. All right. So let's just sort of be clear. Our goal now for finding the native state, as we've expressed before, is to find the minimum energy structure or conformation of a protein. Strictly speaking, we want to have the free energy. We would like to minimize free energy, but realistically, free energies are difficult to calculate. And because they require an ensemble of states, there's a complicated thing to really work with. And so we might replace the free energy with simply the potential energy. And this is based on the relationship between these two. So if you recall, we discussed how the probability of being in a particular state, let's call this, let's call this P of X. The probability of being in conformation X is equal to E to the negative energy, potential energy of state X divided by KT over the partition function, right? And just this, even not worrying about anything else. What does this tell us? This tells us that the single most probable state is the lowest potential energy state. And so the minimum, sorry, potential energy state is the most probable. Now, it doesn't tell us everything. The fact that free energies are important and entropies are important means that in reality, proteins are the native state of a protein is an ensemble of many structures, but one of those has to be the minimum potential energy state. And so searching for this is a very reasonable thing to do, a starting point in solving the protein structure problem in any case. So what does this really mean? The problem we're trying to solve? The problem we're trying to solve then is given some expression for the energy as a function of coordinates of the system. We want to find the X that minimizes E. That is, we want to find minimum X of the energy function. Right? Now, this kind of problem, this class of problem, a minimization, is part of it's a very common class of problem. This is known as an optimization problem. And optimization is a field that has had a tremendous amount of work done on it. Optimization problems, minimization, maximization problems come up in all kinds of fields, and there's a tremendous wealth of methods that we can draw on to tackle this kind of problem, a general optimization problem. We're going to see optimization problems come in repeatedly throughout the semester. And so I want to spend a few minutes just generally talking about optimization problems in general, how we think about them, what the factors we need to consider in discussing them, so that we can think about what methods are applicable here, and down the road we'll be able to understand how much of what we're developing here might be applicable, how much other methods might be able to be used, and so on. Right? So let's talk a little bit about optimization. When we discuss optimization problems, one of the first things that we should always do is think about what kind of space are we dealing with. what kinds of variables are we dealing with? What is the structure of the problem, if we will? Right? So we should ask questions like, are our variables continuous? Are they discrete? Or do we have a mix of them? One question. What kinds of numbers are the variables? Are the variables real numbers? Are they complex numbers? Are they integer numbers? Or are they perhaps not numbers at all? We'll see in the protein design problem that we'll discuss a little bit later, that our space, some of our variables are the choice of an amino acid at a particular position, which isn't fundamentally a number, right? We can have optimization problems in that kind of framework. Those are questions about the variables. We also should ask questions about the nature of the function that we're dealing with. And I'll discuss this a little bit more in a moment. But we want to ask the question, are there local extrema or relative extrema, particularly multiple relative extrema? Oops, sorry about that. My pen sometimes decides to be a mouse. So are there multiple relative minima, maxima, and so on? Or is the problem what we call convex? And a convex problem is one that has only a single well-defined optimum in it. Finally, so we asked a question about the structure of variables, a question about the structure of the search space, and we should also ask the question if there are any constraints on the problem. Sorry, wrong kind of there. Are there any constraints? Constraints could be limits on what the variables can take on. Again, later in the semester when we discuss the dynamics of chemical reactions and things like that, the variables in that context do have constraints. They can't be negative because the negative values don't make any sense. Are there constraints on the problem? In some applications, you may have specific constraints on what variables can be. In other problems, you might have constraints where some other function of the variables needs to be within a certain range or something along those lines. Before going on, I want to sort of highlight this sort of question, this point 3 for a moment. What do we really mean when we talk about multiple extrema? Well, let's just sketch out. What we really mean is that if we have our target function, some function of x with some generalized coordinate, and in reality these are multi-dimensional, but it's much easier to just imagine a one-dimensional surface. If we have a structure, let's imagine a surface that looks something like this. Right. A surface like this has many relative extrema. There are many points on this surface that are local minima. We have a local minimum here, a local minimum here, a local minimum here, and a local minimum here. We also have many local maxima, a local maximum here, a local maximum here, a local maximum here, and so on. These local extrema, maximums, minimum, are lower in the target function than any point in the immediate neighborhood, but may not be lower or higher in energy or in target function than other points. And we make a distinction between local extrema and global extrema, where the global minimum is the absolute lowest of all of the local minima. The global minimum here. And perhaps if this is the complete space, then we would probably suggest that this one here is our global maximum. Now, the reason that we always want to do this is because some algorithms for looking at optimization problems work well in some contexts, but don't work well in others. There are algorithms that only work with continuous variables. There are other algorithms that only work with discrete variables. There are other algorithms that work on any kind of variable. There are algorithms that only work well with well-defined numbers. There are other algorithms that are more generalizable to non-numeric variable types. There are algorithms that are well suited to handling constraints, and there's algorithms that aren't. And perhaps most importantly, there are algorithms that are designed to find local extrema, and there are algorithms that are specifically designed to find global extrema, or at least to attempt to find global extrema. I should actually emphasize the problem of finding local extrema is a problem that has a solution. There are algorithms that can find local minima or local maxima fairly robustly in pretty much any circumstances. There might be performance questions, but the answer can be found. The problem of finding a global minimum for an arbitrary target function that has many local minima is not a solved problem. That is, there are algorithms that in the infinite limit, that in the limit of having an infinite amount of time are can be shown should converge to the actual global extremum, global minimum or global maximum. But as we never actually have an infinite amount of time, it isn't a solved problem. There are algorithms that can find global minima for certain types of problems, or may often find the global minima, and we will be discussing some of those. Okay. So let's now dig into some of these methods. All right, okay. Before doing that, one thing we should note: what kind of problem are we dealing with in protein structure prediction or in protein conformational search? Well, proteins, what are the variables? And when we're talking about the protein structure problem, our variables are the positions of atoms. And the positions of atoms, of course, are continuous real numbers. So these are what we're dealing with. We're dealing with positions in three-dimensional space, which are continuous real numbers. The conformational space of proteins most certainly does have multiple relative extrema. So there are many local minima on the energy landscape. However, the structure of the energy landscape for many proteins seems to have what's often described as a funnel shape, that in some two-dimensional projection of the energy landscape, that there's a shape something like this, that there's a deep, well-defined minimum in our conformational space, but the sides of this funnel are actually very bumpy, and thus may have many relative extrema on them. So at least for many proteins, there's a kind of a funnel-like concave hull, if you will, for the problem, but on that there is a lot of low relative extrema. In the simple protein structure prediction problem, there aren't really any constraints. The bonds do need to be within well-defined bond lengths and angles within well-defined bond angles, but those are enforced by the energy function, so they're not really separate constraints. But there are some protein structure predictions where there may be constraints that you would like to be able to apply, especially if there's some amount of experimental data or other things like that. But for the time being, we will ignore that part. That is, we have a problem that we want to solve where there's multiple relative extrema, however, with a bias in the energy space, searching over continuous real variables. So now let's get into some algorithms that are well suited for exploring these kinds of problems. I'd like to start with a discussion of local optimization. Not because local optimization allows us to solve these kinds of problems. Local optimization alone cannot solve for the global minimum energy structure of a protein, because we know that there's many multiple minima. But understanding how local optimization works helps us with understanding the framing of global optimization problems, and also local optimization is just something that needs to be part of anybody's kind of toolkit of algorithms that you know. And so it's a good one to have. Right? Local optimization is also very, very often used in molecular dynamics simulations as a preconditioning step on the system. Before, if you did an arbitrary, let's say you randomly select a protein structure to start with to try to solve the problem with molecular dynamics. It's possible that your random structure just has some really bad energetics to it. And if you try to do molecular dynamics in a very high energy state, or even not really so much important that the energy itself, but a place where you have a very steep gradient, a lot of forces. The initial forces are very strong, and it can be very hard for even a fairly small time step to keep up with that. It also messes with the temperature regulation and things like that. Right? You get these initial very, very high velocities, and it can lead to messy artifacts. And so a solution to that is to, before doing any molecular dynamics, perform a local minimization so that you're starting out your simulation at a place where the gradients are close to zero. You don't get these artificial initial condition problems that you otherwise may have. So it's worth discussing local optimization. What do we really mean by local optimization? I think it's very important anytime we're solving a problem, anytime you're thinking about a problem, to be clear on phrasing what your problem actually is. What is the problem we're trying to solve? Give a problem statement. The way I tend to phrase the problem statement of local optimization is something like the following. All right. From a given starting point, you can't really do anything local if you don't have a reference point, if you don't have a place to start, right? The whole concept of locality means around some region. You need to be able to define that in some way, typically by simply giving a starting point. From a given starting point, what do we want to find? We want to find a relative or a local extremum. Right? So find a relative minimum. And I'm going to use the language minimum throughout here, simply because in the protein structure problem, we are trying to minimize energy. That's what we are aiming to do. Maximization works in exactly the same way. You basically just change the signs of them around, right? Anytime we talk about moving downhill, change that to moving uphill, and everything kind of works the same. So, but let's focus on minimization. Right? From a given starting point, find a relative minimum that is nearby. And I put that in quotes specifically. What are the key points of this problem statement? Well, one of them is that nearby is a pretty vague statement, right? We're not asking for a minimum that's within a certain distance of where we started, or contained within a certain region, or anything like that. We're just kind of vaguely saying nearby. And what this means is that anytime, as long as we find a relative minimum from our starting point, we can say that we've solved the problem. Right? Most importantly, we are not asking to find the relative minimum that is closest to our starting point. Right? The closest relative minimum is a much harder problem. It actually requires solving really a global optimization problem on some constrained domain of the search space, not a solved problem in general. Right? And this can be a very important sort of nuance, right? Think about your problem statements. If you tried to tackle the problem of local optimization, of trying to find the closest local minimum, you would be faced with a much, much harder problem than being a little bit more loose in your definition of what the goal of the problem is. Given this phrasing, there's a pretty well-defined solution, at least in conceptual terms. The solution in conceptual terms is to move downhill basically until you can't anymore, right? Until you reach a minimum. And if you think about it, this kind of has to work, right? If you are on some, if you imagine sort of starting out in some position on an energy surface, and you only ever move downwards, you only ever take downhill steps, downhill steps, downhill steps, you're going to lower and lower and lower energy. As long as there are local minima in the space, eventually you'll hit one of those, or I should say, as long as there aren't unbounded regions in the space, then eventually you'll hit a point where there are no more downhill steps allowed. That is, you're at a local minimum. So conceptually, we have a very simple solution. Can we phrase this in terms of the language of math as a preparation for actually developing the algorithms? Let's think about how we would do that. So how would we frame this in the problem of math, or in the language of math? First of all, let's be clear in our definitions. Let our target function f of x so let this be our target function. Where x is a vector of all of the degrees of freedom. What does it mean to say we move downhill? Well, this we can phrase as what we want to do is we want to take some x, we want to take a step, we want to find a new position. I'm going to call this x of k plus 1 is x of k plus p, where, sorry, I should have a k here. This means take a step. We want to take a downhill step, and there's actually two ways that we can define this. So we want to take x, k plus 1 equals x of k plus p, such that, and here's two ways we could define this. One way we could define this is simply such that f of x, k plus 1 is less than f of x of k, a lower energy. This is a perfectly fine definition of what it means to move downhill. It's a retrospective definition, though, right? We can't actually evaluate this idea of whether we've moved downhill until we've chosen our x of k plus 1. And so perhaps we would like to have a way of defining downhill that's more local. Another way of defining that is by using the directional derivative. The directional derivative says, let's take the dot product of the gradient of the function at x with the step. And if the dot product of the gradient and the direction that we're moving is less than 0, this directional derivative means that we're moving in a downhill direction. Either of these can mean sort of move downhill. The second is a prospective definition. The only thing we need to know is x and our step p in order to assess this as being downhill. The second needs us actually to have evaluated the energy after we got there. Right? But we have a definition of move downhill. What do we mean until a minimum is reached? We need to know when to stop. Well, strictly speaking, in the formal language, what can we say we've reached a minimum? Well, there's a couple of conditions. The first condition is that the gradient of the function, I'll use f to represent our final step where we stop, should be equal to 0. The gradient being 0 is a necessary condition for us to be at a local minimum. It's not a sufficient condition for us to be at a local minimum. We also, again, to be strictly correct in the sort of language of math, we also need to evaluate the second derivatives of this function. The gradient of f is a vector of first partial derivatives of the function with respect to position. The second derivatives is a matrix. If I call the Hessian of f of x, f, this Hessian matrix must be positive definite. Just to be sort of clear on what the Hessian is, where's my pen? This Hessian, the ijth element of the Hessian is the second partial derivative of the function with respect to xi and with respect to xj. So it's a matrix of all of the partial derivatives. What do we mean by a matrix being positive definite? We mean that all of its eigenvalues are positive. The Hessian is a symmetric matrix, at least for continuous functions, which ours are, which means it has all real eigenvalues, always has a well-defined eigenvalue decomposition, but we need to check that they're all positive. Right? This is formally what we would like to do. As we go through how to actually realize this, we're going to note that these aren't necessarily conditions that we can perfectly check. But it's good to keep in mind what formally our solution should be aiming at. Okay. There are multiple different approaches to actually performing a local optimization, and how they generally differ is in how you choose P. That there's more than one way you can define a downhill step, and that's really the difference between the various methods. The first one I want to introduce is a method that is sometimes called steepest descent. And it's sometimes called gradient descent. And what this works with is really simply choosing our step based on the negative gradient of the function. We define our step to be some constant, negative constant, multiplied by the gradient of the function. The gradient of a function is the direction of steepest uphill slope. So the negative gradient points in the direction of greatest downhill slope. And that's a very reasonable choice to make. Right? If you want to move downhill, and perhaps you want to move downhill as quickly as possible, choosing the steepest downhill direction sounds like a pretty reasonable approach. The constant here then also adds sort of an idea that we want to take a step that's proportional to the gradient. Why might we want to do that? Well, here the idea is that if you're at a position where the gradient is large, that is a place where the gradient is steep, that suggests that you may be far away from a local minimum, and a large step is appropriate. If you're, on the other hand, you're in a region where the gradient is smaller, perhaps that's an indication that you're close to a local optimum, and so perhaps shrinking the steps so that you don't miss that local minimum and jump over it during the process might be a reasonable approach. All right, but very, very straightforward, very easy to implement in a protein structure prediction problem, because the gradient, remember, is also used to calculate forces. Remember that the negative gradient of the energy function is the forces. So in an application of this steepest descent methods to proteins, what we're really doing is we're going to choose a step that is proportional to the forces on that system. In that sense, it's similar. There's a flavor of it that is related to molecular dynamics. However, major difference here, there's no concept of velocity. We're always just stepping directly in the direction of the forces, not with no idea of momentum, velocity, or anything like this. Right? But if we have a mechanism to calculate forces, we automatically can use that same code, if you will, to calculate gradients. They are the same thing, and so you can implement steepest descent very, very easily. How do we, so this is an easy thing to do, to take the steps, right? So the idea is that we would start with some initial condition. So we would begin with x naught, and then iterate. We would find x1 as x naught plus, or perhaps minus k gradient f at x naught, x2 equals x1 minus k gradient f of x naught, and so on, and continue this as we need. Right? Here, again, you notice, although there's a relationship, the forces are involved in sort of guiding the motion. They work in a very different way than molecular dynamics does. This is a position update, but we're directly using the forces, as opposed to how does molecular dynamics work. Positions are updated with velocities, and velocities are updated with accelerations, which are related to the forces, right? So this is fine for propagating the steps of steepest descents, but how do we know when to stop, right? We mentioned before we'd like to stop when the gradient is 0. Right? The reality is we're taking finite steps here. We're not taking infinitesimally small steps. We may never reach numerically equal 0 gradient. Anytime we're dealing with these sort of numerical optimization problems, we always need to define some concept of convergence. When do we believe we've done enough to stop? Right? And so instead of looking for the gradient equals 0, what we generally are trying to find is we want to stop when the gradient is approximately equal to 0. Right? And we can define this in a number of different ways. One of the simplest ways is to look for the norm of the gradient and ask for this to be less than some certain epsilon, where this is generally considered the 2 norm, the square root of the sum of the squares of all of the elements. We also may use a convergence where we look for the largest absolute value of any individual term in the gradient. This is actually the same as what we call the infinity norm of the gradient. That is, in the first case, we're just looking at the, in some sense, an average. What's the overall size of the gradient? Is it close to 0? In this second case, we're asking for every element, every individual element in the gradient to be close to 0. Right? And many other sort of possibilities. There are possibilities where we might try to factor in the magnitude of the gradient. If the gradients are large, maybe kind of or especially if we have a big vector, right? And so maybe for a big vector, it's harder to sort of define what an epsilon is. Perhaps, or if the value of the function is large, maybe the magnitude of the gradients we might expect to be proportional to that in some sense. So we may do something like defining convergence as epsilon plus 1 plus the magnitude of the actual function. And this would kind of give a more relative convergence, asking for the gradient to be small with respect to the magnitude of the function, where this 1 is added in here just to solve the problem of this being 0, so that we don't have an inconsistency there. Okay. And other approaches. The most important point is that you need to have a convergence check in your algorithm, or else you will never stop. And you should not simply use request that you numerically get a gradient of 0. We discussed the idea of the Hessian. Should we check it? We might ask, should we check the Hessian of the function after stopping? Well, we kind of should, but we also have to be realistic. Let's think about how big this is. This is a matrix of partial derivatives of the with respect to all of the variables in the system. For a protein with n atoms, that means this is a 3n by 3n matrix, where n is the number of atoms. The number of atoms may be in the thousands, tens of thousands, even larger. Performing an eigenvalue decomposition on a 30,000 by 30,000 matrix is a tremendous amount of computational expense. It's a very expensive thing to do. And so it's very often the case that we do not bother checking with the checking the Hessian. Right? How much of a problem is it? Well, if our algorithm is designed where we have to be moving downhill, it's impossible for us to get stuck at a maximum instead of a minimum. Right? It just can't be. You can't reach a peak by moving downhill. Right? So the only possibility, if we accidentally sort of stopped, right? If we reached convergence and we were not, in fact, in a minimum, there's two possibilities how that could happen. One is that we actually reached a saddle point instead of a minimum. Again, the chances of that happening are really incredibly low. In order to reach a saddle point, you have to very carefully walk along kind of a very specific line to get there. It's quite inconceivable that you would accidentally end up at a saddle point, at least in most cases. And so maybe there's a very, very slight worry there, but nothing too major. More likely, the issue you run into with stopping in the wrong position is that you're on a very, very flat surface that has very little slope to it, and so maybe you're far away from a true minimum, but you've hit the convergence criterion. A Hessian check could actually be informative there. It could show you that if you have very little curvature, or if you have some dimensions with very, very low curvature, that may be suggestion that you're in sort of a very, 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 very flat region. But if you are, there's not really a lot of solution to that. And so in most applications, people just tend to completely ignore this check, saying really that it's too expensive for the information you get out of it. And that if you're concerned you might be at a saddle point, you can more easily double check that by randomly moving away from where you stopped in a few different directions and asking, and then repeating beginning the algorithm again, and asking, do you return to that point, or do you move away? Right? So there's alternatives to this check that are easier. Okay. Steepest descent is an easy algorithm. It's an important one to have in your toolkit and to know about. It's used fairly often as sort of a quick and easy optimization approach, local optimization approach. It has some benefits, has some deficiencies. It's really good at very quickly getting in the general vicinity of a local minimum. This step size proportional to the gradient means that it moves quickly at the beginning of the algorithm. However, it has a tendency, again, for exactly the same reason, this proportionality to the gradient means the step size slows, gets reduced as you approach the local minimum, and it can then take actually final steps of convergence can take a long time. So in operation, it's best to use steepest descent with a relatively modest convergence criterion. Don't ask too much of steepest descents. Don't ask it to get you to kind of within 10 to the minus sixth machine precision of 0. Ask for it to get close, and then perhaps use other approaches to get the rest of the way. What are some other approaches? Let me introduce one other approach that I think is a very elegant one, very broadly applicable in a lot of different applications, and where it can be applicable in proteins, protein structure searches with at least with a little bit of a tweak to it. And this is Newton's method, or Newton-Raphson. Sometimes called Newton-Raphson, sometimes simply called Newton's method. What this does is tries to choose P in a more intelligent way, a smarter way than simply saying, let's look at the gradient and follow the steepest downhill. And instead what it does is it begins with the quadratic approximation to f of x. What do we mean by that? We mean the second order Taylor series. I believe that I mentioned in our discussion of we introduced forward Euler that the Taylor series expansion is something that is used over and over and over again in many, many different applications. Here is one of them. So what does the Taylor series expansion look like for our target function? And in particular, what we are going to do the expansion of is the expansion trying to find this xk plus p. Remember, this is exactly how we wanted to define our next position. And we can get an approximation to what this should be by taking the Taylor series expansion. And we're going to do this around the point xk because this is what we know. Now, in the development of forward Euler, what we were working with was a vector function of a scalar argument. We had position versus time, but we have many, many positions, a vector of positions dependent on time, a vector of velocities dependent on time. Here what we have is kind of, that's flipped around. We have a scalar function, energy, but the argument of that function is a vector. So we have a scalar function of a vector argument instead of a vector function of a scalar argument. The Taylor series expansion holds in both cases, but it looks a little bit different. Conceptually, it's the same, but the notation and the details are a bit different. Right? So let's think about what this is. Remember, the first term is the 0th order derivative. The second term in the Taylor series involves the first order derivative. What's the first order derivative of a vector, of a scalar function of a vector argument? Well, there's many. We have a vector argument. There's many partial derivatives. In fact, there's n different partial derivatives if we have n entries in X. The set of all of those is the gradient. Right? This is exactly what we mean by the gradient, and I'm going to put a little X under here for reasons you'll see later, to emphasize that we're taking the gradient with respect to the variables of X at xk. So the gradient of f at x. Right? And if we sort of, let's just sort of make a comparison to what the Taylor series looks like for a scalar function, and let's just do a scalar function of a scalar argument, right? If we wanted to do some scalar expansion here, what would it be? It would be f of x plus f prime of x times p, our shift relative to our expansion point, and then a second derivative piece, the 1/2 second derivative of x p squared, and so on. Right? So what should this first order term look like? Well, it should have our gradient, but it should also have the vector of interest, our step. Now, the gradient is a vector. This is a vector. We need to end up getting a scalar. The energy is just a scalar. We get this. How can we evaluate this product? Well, we do this by essentially taking the dot product, or thinking of taking the transpose of this vector, multiplying by another. A dot product of the gradient with the direction we're moving in. Remember, in fact, what this really is, this is the directional derivative of the function in the direction of p. Now, what about the next piece? The next piece is a second order derivative. The second order derivative of a scalar function of a vector argument, right, is the set of all of the second derivatives, second partial derivatives of this. We've already discussed what that object is. That object is the Hessian of our function evaluated at xk, right? The matrix of second derivatives. We want to be quadratic in p, that is, we want 2 copies of p, but we also need to end up with a scalar. Right? Again, So for this to work out, right, we want a scalar argument. We're summing. We need to sum scalar terms. The first term is a scalar itself. The second, we have first derivatives. We can get that to be a scalar by multiplying by p in the dot product. How do we get scalar in the same way here? Well, we can do this taking P transpose times the Hessian times P. This structure is a very, very commonly seen construct in linear algebra. It's reminiscent of the form of an inner product and returns a scalar from the product of two vectors with a matrix. We need our half scaling, just as we did here. You can actually, it turns out you can actually continue this expansion. It becomes a little bit messy because the third term here, the third term for third order derivatives involves a third order tensor for the as the structure of the derivatives, and you need to somehow multiply that by three matrices, or sorry, three vectors to get a scalar, and there's no clean notation to do that. But luckily, we don't need that for this because we're only taking the quadratic approximation, so we can stop right here. What can we do with this? Well, we're going to start with the quadratic approximation, and what we want to do is we want to minimize this. Okay? This is an approximate value of the value of the function after we've taken the step. And so we can think about minimizing this. Minimize. And what do we want to minimize this with respect to? We want to minimize this with respect to P. Why would we do that? Well, this would then say, given this approximation, what is the P that will give us the smallest possible f? Right? This is exactly what we're trying to do. We're trying to find the smallest possible value of the function. So we're going to try to minimize this. Now, you might say, well, how does this help us? We were already trying to minimize a function. All you've just given us is another function to minimize. This helps us because this minimization can actually be done analytically. Right? How do you find a minimum of a well-defined of a single-valued function? Or sorry, not a single-valued function, a function with a single minimum? You can take the gradient with respect to P. Now, the set of all partial derivatives with respect to P, and set that equal to 0. It doesn't make sense if we try to do this if their original function, if we just try to set the gradients equal to 0 and ask what the answers are. It's a multiple minimum problem. There are hundreds, thousands, perhaps hundreds of thousands of answers to that. And there's no clean way to find them. It's not an expression we can work with analytically and actually find those answers. So we're stuck with numerical approaches. Right? This is not that kind of function. Right? What are we trying to do? We have a very, very simple function of P. There's a constant term, a linear term, and a quadratic term. And so when we take this whole expression and we take the gradient with respect to P, Let me make that a little bit more of a clear subscript. We will end up with something much simpler. So what happens when we take the gradient of this with respect to P? Well, let's think about it. The gradient, we're really taking the set of partial derivatives with respect to P. X of K is a constant. That is a constant vector. So the derivative with respect to P of f of xk, this is just a number, is 0. That piece disappears. The derivative with respect to P of a linear function in P is simply the gradient of f at k. Derivative of x is 1, right? Derivative of k of x is k. Exactly what we have here. So we have 0 plus the gradient. What's the derivative of this piece? This piece behaves just like a quadratic. This expression is quadratic in P. 2 copies of P and a constant matrix, as well as a factor of a half. And this, what happens when you take the derivative of a quadratic, you get a linear form. Exactly the same thing happens here. The gradient with respect to P of this Hessian term is simply the Hessian evaluated at xk. Again, it's the matrix of numbers times P. And this is what we want to set equal to 0. We want to take that sum equal to 0. What does that lead us with? Taking that sum equals to 0 gives us a that these two terms have to be equal to each other but opposite in sign. So we end up with the Hessian evaluated at xk times P has to equal the negative gradient with respect to x evaluated at xk which we can now isolate P, and P must be then given. Pen's just being a little bit slow, sorry here. Must be given by the negative inverse of the Hessian matrix. Multiplied by the gradient evaluated the same position. So this gives us an update that would directly solve for this quadratic approximation. Right? This method can be incredibly efficient it can find optima, it can often find a local minimum in a very, very small number of steps. And for many applications, it's a really, really great method to use. Right? There's one big challenge with this for applying this to protein systems, and that is, that it requires the inverse of the Hessian matrix. We mentioned in the previous slide that the Hessian matrix is big. It might be thousands by thousands of elements. For not checking for the Hessian being, the eigenvalues being positive. In the previous case, we didn't do that because an eigenvalue decomposition of a massive matrix is expensive. An inverse of a massive matrix is expensive. Also, it is prohibitively expensive to calculate this Hessian matrix. Also, it's not clear that we actually have an analytical form for the Hessian, and it may be even very expensive even just to calculate the Hessian matrix, let alone to invert it. So we have a method that is very powerful, but is hard to use for a system with many, many variables. Systems with fewer number of variables, this is a fantastic approach to keep in mind. So how might we get around this? Well, there is an approach that can be used, and we can start by, let's think about what the methods that we have sort of looked at so far. Right? We had steepest descents, and steepest descents gave us a great step of the gradient, and you have often a scaling factor, but let's consider just the simplest case of a scaling factor of 1. We're actually going to step exactly in the direction of the gradient. Okay? And we might think of what is, well, I could put a K in here anyway. What is Newton-Raphson doing? Newton-Raphson is replacing this K with a Hessian, right? Or rather the inverse of the Hessian. Sorry. So we can sort of think of this as, well, let's compare these. In steepest descents, we're still using the gradient, but we're just always scaling it by the same amount. We never change the direction. We always move in exactly the direction of the gradient, and we always change it by the same amount. We always scale its length by the same amount. Right? What are we doing in Newton-Raphson? We also are using that gradient information, but we're scaling it by a matrix. This means that, first of all, that the degree to which we change the length will vary in different steps depending on what the Hessian is. And also the direction might change a bit. Right? If we think about it this way, if we think about the Hessian really as being a dynamic scaling factor that can shift direction as well as the magnitude, And the ideal case being where this is the Hessian that we sort of just discussed. Maybe there's a middle ground. Maybe there's a middle ground where we can find something that is an approximation to the Hessian, something that is close, that contains some of the information of the Hessian, but maybe not all of it. And that would still be a step up from just a constant scaling factor that doesn't allow us to change direction, right? Even including some of the information of the Hessian would very likely be an improvement over this non-dynamic scaling that we have in steepest descents. And this is a idea that is sort of captured in a method known as adapted basis. Newton-Raphson what we do is we compute an approximate H inverse that we can think is close in some sense to the true Hessian, but much, much easier to compute it. Right? The way this is generally done is if we think about the full dimensionality of the problem, this full Hessian is not only a 3n by 3n matrix, it is generally a full rank matrix. The rank of the full Hessian is 3n. Full rank matrix, very, very difficult to invert. What we are going to be replacing this is with a very low rank approximation. Rank, let's call this a rank R matrix, where R is usually on the order of 5. Right? Very, very, very small. So 3n might be 30,000, 100,000. We're looking at a very, very low rank approximation to this matrix. And the way that this is done is by looking at only a small portion of the overall space. How can we define kind of a reduced dimensionality space to work in? Well, what adapted basis Newton-Raphson does is take the last R steps. That is, take the vectors P from each of the last 5 steps. So kind of we're taking P minus 5, P minus 4, P minus 3, P minus 2, and P minus 1. Right? This is a set of 5 vectors, and these 5 vectors span a 5-dimensional subspace of the full 3n space. And what we do is that we compute the Hessian in this subspace. So we might sort of take this, we take the span of this, this gives us a subspace that I might call S5, and we're going to compute the Hessian in this S5 subspace. invert it in S5, and then sort of embed that back into our original space. I don't want to go through the details of how exactly we do this. A little bit later in the semester, we're going to explore these matrix, this rank-reduced matrix approximations using tools like the singular value decomposition, and we will get into the details of exactly how we can do these low-rank approximations when we do this. Right? The key take-home here is that an approximate Hessian can be computed, an approximate inverse Hessian can be computed, and we use that in place of the true Hessian, and that gives us something that is both accessible from a computational cost perspective, even for protein systems, and yet has many of the features of the full Newton-Raphson, and is a very powerful method. All right. So I'm going to stop our video here. What we've discussed in this video is two approaches to local optimization: steepest descent and Newton-Raphson, as well as its slightly modified form, adapted basis Newton-Raphson. And what we will be shifting on into the next lecture will be a discussion of some methods for addressing the global optimization problem. These local optimization methods aren't really applicable to solving the full protein structure prediction, as I mentioned earlier, but they are an essential piece of the puzzle. They're used for preparation of structures. They can be steps in full global optimization. And so I think the time we spent discussing them was worth it. With that, I will say goodbye for now. Take care and be well until I speak with you next.